In this section, we're going to cover Chapter 6, so you'll need the Chapter 6 notes. Something else you'll need from Blackboard, go to Notes, and then Tables, it's at the top, and download the Z distribution table document. You can also get this from the appendix from your book. I've just already gone ahead and put it in a Word doc to make it a little easier. So we're going to talk about what this table is and what's in it, and then when we get back to class, we'll talk about how to use it and do a bunch of examples. So we ended last time with probabilities and hypothesis testing, and the sort of how do I know when things are weird enough to be able to reject the null hypothesis. Because remember, the point is, even though we have these two hypotheses, the null where there's no difference, and the research hypothesis where there is a difference, that we want to be able to reject that null, to say that the likelihood of that happening is so low, that the data is so odd that it can't possibly be true, and instead our research hypothesis must be true. And so we talked about p-values and how probability is calculated as like success over the number of outcomes. But in this section, we're really going to move to using probability as more of a distribution and a percentage. And so probability often is calculated in an objective way, where you run a test 1,000 times and look at the number of times that something happened. Or we can think about it subjectively, like the likelihood of something happening. And it says statistics fall somewhere in the middle, where we don't run things 100 times anymore, so we approximate. So we're getting into being able to use the normal curve and z-scores to approximate probabilities to be able to do hypothesis testing in the next section. And so we're learning a new way to get at how is the null weird enough, and so I would be able to reject it, which is what we want. Remember, we want to reject the null because that means that our research is true or supported. Right. So this is the normal curve section, along with standardization and z-scores. So the first thing that your book has is a section from Freakonomics, and I will send you the link through Blackboard so that you can watch the video. It's really short. And so they talk about this teacher cheating scandal that happened in Chicago, which many teachers got fired because they were cheating for their students, because they're under a lot of pressure to be at a high-performing level. So if you're looking at the data that they received to help determine if people were cheating, there's just thousands and thousands of data points. So how do we know that that happened? What they were looking for was a very low probability event. So let's look at the likelihood of these things happening in this way. And so they found that teachers were cheating by looking for something that was so odd, the probability of that happening was so low that it couldn't possibly be by chance, and that would be the null, is that it was by accident or by chance or by all these other reasons. But the likelihood of the teachers having all those same patterns was so improbable that they had to say, well, it has to be cheating. And the video talks about that and gives you some examples of how they did the cheater detection. And so that part is from the original Freakonomics. But where we're going to start is with the bell curve. And so this is the bell curve. And what they were trying to do is calculate the area under the curve, which is much easier now with the computing power that we have and some handy calculus. And so they were trying to figure out like how much is between these 2 points. And so that's how much probability occurs between those two points on the curve. And so, it's been around since the 1800s, starting with De Moivre and Bernoulli. And they were trying to find ways to approximate answers so that when you're calculating probability, you wouldn't have to do it tediously by hand all the time. And so the bell curve usually is used to describe IQ, but that's not the only thing it applies to. But it's something that happens that you're familiar with, but it has been around and been used for quite some time now. What we do now is we talk about it as the normal curve, which is sort of amusing since it's not the most normal thing to happen. But remember that this picture is a histogram, so everything here along the bottom are values, okay? And everything here up this way on the y-axis is frequency. So the top piece here are the most frequent scores. So remember, this would be the median, the mode, and the mean, because a normal distribution, they're all the same. So in a normal distribution, we can split the whole thing in half, so this makes it symmetric. And symmetric distributions, you can do a hot dog fold, and they are even on each side, so that means there's 50% over here, so excuse my terrible drawing, and 50% over here. And that's really useful to have half the probabilities and half the scores on one side and half the probabilities on the other side, so we're going to use that to our advantage. Now, we could have any set of values along the bottom, but to make our lives easier, we're going to make the middle 0. We've talked before about how 0 is not necessarily the most useful number when calculating standard deviation, but in this case, it's going to be a very useful number, and we'll get into why here in a second. Okay. And so the normal curve is always going to be with the highest frequencies in the middle and just little bitty low numbers out here on the sides. So it is going to be unimodal and symmetric with 0 in the middle. And so how do we know what this normal curve is? Like, how does that work, and how does it happen, and why is it the normal curve? Well, let's say we decided to take a sample of a small number of people. So this is a sample of 5 people in this picture. And we've calculated their heights. So here are our values along the bottom. And we've calculated the frequency of those heights here. Come on, computer. Up the y-axis. So this is, again, a histogram. And you'll see that we have a unimodal curve, so one hump. And it's kind of normal. We don't really have quite enough people to say that this is the most normal curve. But we're starting to get that sort of normal distribution. So height is very normalized. Well, 5 people is not the most useful sample because small samples aren't totally representative of the population. Right? So let's take more people. So I want you to hang on to this number here, 30, because 30 is a magic number. So when we get into the central limit theorem, we'll talk about how by doing a lot of these objective probability calculations and running lots and lots of simulations, we found that 30 is sort of the magic number in statistics where things seem to go right. And so in this distribution, we are getting more normal. And so we have, oops, can't work my computer today. A one hump distribution with the most people in the middle, and then just a little bit here on each ends of the tails. And so it's got some people missing here, but because it's not perfect, it's still a sample. But we're getting to be that unimodal and symmetric properties of a normal curve. And then the more people you take, the more normal it's going to be. And so, as we add larger and larger people, and we get a bigger sample, the distribution will slowly become more of that idealized curve, where you get lots and lots of people clustering in the middle and very few people on the outside. So this gives you that idea of it being one hump overall, with only a couple people here on the outsides, and it's fairly symmetric in the middle, where we have half of the scores on one side and half of the scores on the other side. And so what that set of slides is trying to show you is what's called the central limit theorem. And that idea is that as sample size increases, the shape becomes more normal. Okay, so as sample size goes up, the distribution becomes more and more normal. And so that really helps if you start with a skewed distribution. That's one way to fix it. So if we're wanting a normal distribution, you can add more people. But definitely 30 is the magic number. So at 30 people, we're close enough to the normal distribution to say, yeah, everything else is okay. And so we're going to use that as a way to determine if we're close enough to normal for our hypothesis test to be accurate. And so what might be some things that are normally distributed? Okay, and so a really great example is IQ, because we sort of force intelligence quotients to be on the normal distribution. That's why when you say of a bell curve, people think of IQ. Also partially because it was a really terrible book about IQ differences in different ethnicities. But it is very normally distributed. You have lots and lots of people that cluster around the middle, and then very few people in the tails, where we have genius and mental disabilities. And so IQ is one of the most normal distributions that you would see, but any standardized test that you might take forces a normal distribution. So the GRE, the ACT, the SAT, if you like those personality tests, they all sort of make normal distributions happen by the way that they ask their questions, so that they get most people in the middle where they're wanting their scores to be, and then very few people on the outsides. And that's really useful if you're trying to use them as a way to determine you're going to take the top 10%, or maybe you're going to use a screening test and take people in the bottom 30%. So let's say you have a hearing screening test, and you're trying to determine who might need some sort of hearing aid or hearing loss, special things. What you can do is take a test for that, and they will look at where you fall along a normal distribution. And if you are very low on your scores at the bottom, they're going to sort of help you out. That's also how we do the remedial math and English classes at the university, is we sort of look at people's ACT scores and we say, you know what, you really need to take this other class first. It's also how many of you probably clubbed out of the lower level math classes here. Okay. So there are lots of things that are normally distributed: height, weight, IQ, hearing. So it happens a lot in our surroundings. You're just not totally aware that they're normally distributed. You don't think about it that way. But the other important thing to think about is this thing. So what kind of variables are we talking about when we're really focusing on the normal distribution? Now, I've said histograms don't discriminate. They like all types of variables. But when we're moving into this section, we're really talking about scale variables only. And so we need the data to be either interval or ratio distributed to make a normal distribution. Because if you think about things like, okay, gender, that's going to be, this many men, this many women. There's almost no way we can force the normal distribution on that, because it's going to be square. It's going to be a rectangular distribution. And if you think about, let's say, religion, why are we putting this religion here versus this religion here? So we can make it look normal, but there's no rhyme or reason to the scale on the bottom. So what we want to do is use interval or ratio data when we're talking about normal distributions, so that we can calculate those p-values, because they have a logical ordering on the x-axis, where the lowest values are on the left and the highest values are on the right. And that's where Pareto charts really come in, is Pareto charts are kind of better for categorical data. Remember, those were histograms where they put the tallest bar first. So they have their purpose for more nominal data for a histogram, but really we're going to focus on histograms for scale type data. So why would I use the Z distribution? We can use the normal curve without standardizing it. So we could make the a histogram of our data and say, look, it's a normal curve, let's use that. Well, the good thing about using the Z distribution, or the standard normal distribution, is that it lets us compare. So this goes back to our apples to oranges. And so if you aren't sure, why do we use standard deviation? Why do we do this? A lot of the times the answer really is, I want to compare things. So we are working on looking at our master's applications for graduate school, and sometimes what will happen is we'll get people who have scores on the old GRE system, which is an 800-point scale, and then a lot of scores on the new GRE system, which is a 170-point scale. They are totally different things, and they're not comparable really if you just look at them. We have the same problem at the university if people take the ACT versus the SAT. So there are lots of times when you would have multiple scales and you want to compare them. So standardization, or the standard normal curve, or Z, allows us to compare them by creating that shared distribution. So if I'm using a histogram, what I've done is taken my histogram, and instead of it being on a 0 to 800 scale, right, what I can do is take the whole thing and move it to where a 0 score is in the middle, and now I can compare my 0 to 800 scale to my 0 to 170 point scale. So what creating Z-scores does is really allows us to put everything on a shared metric system, and that makes a lot of things easier. By converting to Z-scores, it also allows us to create percentiles. And so if you were ever told you were in the top 10% or the 90th percentile from a test, what they've done is converted your score to Z and talked about the p-values. So we're going to use percentiles and p-values, and they mean the same things. Percentile is going to be where it's multiplied times 100, or you can do it as p-values, which are always listed in proportions. And so they really do, they're sort of interchangeable, they're just where the decimal is going. Alright, so we've talked a couple times about there are a lot of terms for the same thing. And so what you'll want to do is really make yourself a chart or something of all the different terms. So the normal curve, the standard normal curve, and the Z distribution are all the same thing. And so it can get confusing. I'll try to call it Z or the normal distribution, but the standard normal distribution, all of them are talking about that pretty bell curve. So we're going to talk about a couple of different things in this section. Mostly, what is the Z distribution? Why are we using it? What makes it special? So what are Z-scores? So the scores on that individual distribution, and how can I compare those Z-scores? And then how does that get me back to P? Because remember, the point is to be able to get a percentile or a probability to be able to do hypothesis testing. And so this section is going to seem like a lot of little bitty math pieces, but the overall big picture is we're trying to find a way to calculate those probabilities to determine if our null hypothesis is false, or which would support our research idea. So we're getting to this bottom component. That's like the thing we want the most here. Okay. All right, so I'm going to save you the sadness of drawing it and show you on a slide or two ahead. It's this thing. Okay. So what is the Z distribution? Well, it's a normal curve where we have stuck the mean to be 0. Okay, so we're putting 0 here in the middle, and we'll go back a couple slides and talk about why. And then that means we've created a distribution where there's 50% on one side and 50% on the other side. That also creates a standard deviation, if you will, where each sort of block of the distribution is one standard deviation apart. So this is the Z distribution. Let me back up a couple slides and talk about all the parts to the Z distribution. Right, there we go. So the Z distribution is the normal distribution. It's also called the standard normal distribution. We've said that a couple times now. Okay. And so what are Z-scores? Like, how is this distribution calculated? Well, a Z-score is calculated with this over here. And so it is the number of standard deviations away from the mean of a particular score. And so what I really want you to do is make that symbols chart that we've talked about a couple times now. And so let me talk about each piece separately. So the first one is X here. Remember that X is an individual person's score. So it's one score for one person. Now mu, this little fancy U, we haven't used too many times, but mu is the population mean. Okay, remember that Greek symbols, the joke is it's Greek to me where they got it from. So Greek symbols are numbers that they will have given to you. So you don't calculate mu, even though it's a mean, it's just it's given. So when you're thinking about IQ, mu is 100 points because they have forced IQ to have a mean score of 100. And then sigma here, little swirly O, is the standard deviation for the population. So we're using two population terms and one individual person's score. And so if my sigma is also going to be given to you. So remember that standard deviation is the average distance from the mean, where most of the people's scores are between one below the mean and one above the mean. And so if you have, for IQ, you have a mean of 100 and a standard deviation of 15, that means most people's scores fall between one below, so 85, and one above, 115. So a big block of people are between 85 and 115, and we can actually tell you the exact percentage because that's the point of a z-distribution. And so z-scores are the standardized score that tells me how far away from the mean you are. That's this first part. Okay, so the raw number just tells me how far above or below the middle your score is. So if your score is a 1.2, then you are a 1.2 standard deviations away from the mean. The other part to z-scores is if they're positive or negative. Okay, so if they are positive z-score, that means they're on this side of the distribution. So remember that we are setting up our histogram to have 0 in the middle, negative scores on the left, positive scores on the right. So a positive z-score means they're on the right side and they're above the mean. A negative z-score means they're on the left side and they're below the mean. So z-scores really have two parts. It tells you the strength, how far away are they, and then it tells you the direction, which way are they? Are they above or below the mean? Which makes them super useful. So hang on to this formula, we're going to use it a bunch. So here's my picture again of the z-distribution. So one big thing is to memorize this. It's also on the next slide. That's how many times, how much I think it's important. But because we set up the formula here as x minus mu. So think about this for a second. Let me go back here. If I told you that the mean of the new GRE system was 150 points, because it is. That tells me that's the sample mean, the population mean, so it's mu. Right. If I take all the people here, so these are my x values, and subtract that population mean, mu, 150, that means everybody who's here at the middle in the mean now has a score of 0. And so we've created the middle to be 0 by taking each person's score and subtracting the most scores, the mean. And so that takes the distribution wherever it was. It used to have a middle of 150 and just shifts the whole thing to be centered over 0. Because 0 is now a very useful number. If I tell you my z-score is 0, you know exactly where I am. I'm on the 50th percentile because I'm right in the middle. So 50% of people are above me, 50% of people are below me. And it also can tell me what my score was. So if you told me that the mean was 150 and I have a z-score of 0, I must have scored a 150. And so really all we're doing with this standardization, this normal distribution stuff, is taking the original scale along the bottom and converting it to a scale where 0's in the middle. Alright, so that gives me the x minus mu part. What happens when I divide by sigma? So when I divide by sigma, that's what creates these z standard deviations. Because remember, sigma is the standard deviation of the population. And so it's, how much is normally here between the mean and the average distance around the mean. So if I tell you that sigma for this distribution is 5 points on the new GRE scale. Okay. What that means is that for each one z-score, the scores here are 155 and 145. Okay. Because that is one standard deviation below, so 150 minus 5 is 145, and one standard deviation above, 150 plus 5, 155. Okay. And so that makes these numbers nice and even, so 1 and 1, to represent one standard deviation above and one standard deviation below. And so instead of it being in the scale, the original scale, where it's 5 points above and 5 points below, I can just talk about it in standard deviation units. So that's why z-scores are the number of standard deviation units they are away. So it takes out the original scale and makes it the same scale for everybody. Okay, so I could do this whole example again, and now talk about the old score. So the old scale, the mean was 400 points. Right? So I got 400 here in the middle. So that's x minus mu. So mu is 400. So everybody, that's a mu and not an n, who had a GRE score of 400 was now centered over 0. And the sigma, or standard deviation, was 100 points. So if I got a z-score of 1, that meant that I had scored a 500. If I got a z-score of -1, that means I had scored a 300. So one standard deviation below, one standard deviation above. And if I had the original scale on here, remember it's 150, 155, that lets me compare a score of 500 to a score of 155. I know that those things are approximately equal because they both have a z-score of 1. And so that really was the beauty of z-scores, is that being able to compare and then also the percentiles. Okay. So this is super important. This is a very easy question on your homework, on the test, on the quiz, so don't miss it. It's the mean of a z distribution, the mean of z, not the mean of the original scale, because z is standardized, is always 0, always, always, always. Okay? And the standard deviation of z is always 1. And that's because we forced that formula on it. So even if you don't totally understand math here, if you do this formula and subtract the mean from everyone's scores, it makes those deviations 0. Remember, that's why we got to square it in standard deviation. It's because otherwise it all adds up to 0, and that's not helpful for standard deviation. Now it's super helpful for z. If I then divide everybody's score by the average number of deviations, that makes the standard deviation 1. Okay? Because that's, in general, people are at least 1 standard deviation from the mean. So the mean is always 0, the standard deviation is always 1. Now, I moved this slide up. It's not going to be in your notes. It's going to be a little bit later, but I wanted to give you kind of a preview of what's going on. And so there are lots of different things I can do with z-scores. And what we'll do in class next time is work a bunch of these examples so that you can do the homework and the quiz kind of a little bit easier. Okay? So I can find a z-score. So I'll give you the raw data and a mean and a population standard deviation and say, what is z? And that's like the easiest step. You can also backwards convert. So if I give you a z-score, I can figure out what's my raw score. And that's something that you need to make sure you get is that X and raw scores are the same thing. So we don't tend to talk about it as raw scores, we tend to talk about them as one person's score. But if you ever ask for a raw score, they're saying what in the original scale did they score. So that's taking it back to the original scale and not the z-scores. And then the rest of these are all about percentages. Okay, so this is where P comes in, or what we're trying to get to. So we can do hypothesis testing. So I can find the percent above a person. So if I create my little distribution here, I can look at, if your score is here, I can look at percent above. So how many people are scoring above you? I can look at percent below. So how many people scored below you? I can do percent between two numbers. So if I have a score of 1 and you have a score of 2, what's the percent of people that score between us? If I'm given a percent score, I can find your z-score. And then probably the most complex one, although it's not that hard, is if I'm giving you a percent, I can find your z-score and then your raw score. So this given percent thing really takes me back to this formula up here. What's the raw score? So if I can go from percent to z to raw. So all these different types of things are the different types of questions that you'll see on the homework and the quizzes. And so I just want to give you a preview of here's all the possible combinations of things that we could ask. Okay. And they're just variations on a theme. So let's start with find a z-score. Now, that's actually very easy with this formula. It's just some plug and chug here. So I would fill in the person's individual score, the population mean, and then the population standard deviation. So let's do that for an example. I'm going to switch to Word so you don't have to deal with my bad penmanship. And let's say I have my old GRE, right? And I know one person scored a 700 on the math component of the old GRE. So that sounds pretty good. It's close to the top. They have, they're close to the 800 limit. Okay. I told you that the, let's just call it mu here, population mean, or mu, the little u, was a 400. And then sigma, the population standard deviation, was 100. So that means to calculate their score, I would do 700 minus 400 divided by 100. And that would give them a z-score of 3. Okay. So they are 3 standard deviations away from the mean, and that's a lot. Now let's say I had the new GRE, and we had a person who scored a 165. Or let's do a 160, actually, so we don't get the same number twice. So 160, they're above the mean. So the population mean for this old scale, or the new scale, is 150. And the population standard deviation is 5 points. So that means that their score would be the 160 minus the 150 divided by 5. And that would be equal to 2. Okay. And so that tells me that they're both above the mean because the scores are positive, and that the first one is better because the score is bigger. Okay, so it has a larger magnitude. And so converting to z-scores is just a bunch of plugging and chugging. And the worst trouble that people have is that they get x and mu backwards. So make sure you always put the person's score first and the population score second. Now, what I could do additionally is go from a z-score to the raw score. Now this happens a lot when I maybe have, usually you'll have the percentiles instead of the z-score, but instead, let's say someone asks me, well, what do I gotta make on the GRE to be in the 90th percentile? Or what do I gotta make to be 2 standard deviations away from the mean? Like, what kind of score do I need to have? And so people are trying to be, at the top or at the bottom, depending on what the scale is. And so this is where you might say, well, you need to make this type of score. So if I am trying to tell somebody, okay, I know on the old GRE, I had to make a 700 to be in the third standard deviation away, or a Z-score of 3. But if on the new GRE I want a 3, what do I got to do? So that one is, I'm going to look for the raw score by plugging in a Z-score of 3 with the same mu and sigma. So that formula is that the raw score is that Z-score times sigma plus mu. Okay. Which is the same thing I got over here on SPS, in PowerPoint. And also a plug and check problem. So I would say 3 times sigma, which in this example is 5, plus mu, which is 150. So that means they need to make 165. So if they want to be comparable to my first person here who has a Z-score of 3, they need to be making 165. Okay. And so the reason that we might be doing these sorts of things is to make comparisons. Okay, this is apples to oranges. We really want to be able to compare things because that's the point of statistics, knowing how things are different, if our research and our null hypotheses are happening. And so we're moving to ways that we can make comparisons. So if I know my score on this exam, so if I scored a 700 on the old GRE, and I have my friend's score, but on a different exam. So he scored the 160. And normally we wouldn't have a way to compare that. So we're going to take them and convert everything to the Z-scores and figure out who did better. So if I made the 700, that means my Z-score was 3 from our example. And my friend made the 160, and their Z-score was 2. I am killing it. So I have the higher Z-score. So if you get asked who did better, you want the score that's higher. Who did worse, you want the score that's lower. And so you just calculate both of the Z-scores and look at them. Okay, and remember this is a standardized scale, so I can just compare them directly to each other at this point when they're in Z. Right, and that's really the summary for this section, is that the point of Z is to compare apples to oranges. So I love this phrase a lot. We're going to use it throughout the semester. And so standard deviation really is being able to compare scales. How much do people vary around the mean? Z-scores are exactly that. They're for standardized purposes. There are a bunch of other examples of that we'll get through the semester. And so if you get asked why would we do this, it's for comparison purposes. So we're going to talk just a touch about how Z relates to P, and then we'll do a bunch of examples in class. So really, like calculating the Z-score and comparing you and your friends are sort of cute examples of what Z does for you. But really the power of Z, the power of the normal distribution, is getting us to hypothesis testing. And that is all about percentiles and p-values. Okay. And so this is what the table is for, so you're going to want to pull that table out. So Z-scores tell you where something is on the distribution. So it tells me how far away from the mean and if it's above or below. But because this is the normal distribution, and people have already done all the calculus for this for us, we can actually tell how many percent of people are above and below. And so we can use that area under the curve to calculate percentiles. So let's look real quick at that Z table. And so the point of this glorious table, let me make it bigger here, is to show us what those percentile ranks are. So let me talk about each piece kind of individually. So I'm going to look here on this first column where it just says Z. Okay, so the very first column is the Z-score. This is X minus the mean divided by mu. So whatever score that you have calculated is in the first column. Now the book representatives are kind of lazy, so they made the chart double columned. So when you get to the end of this picture, go up here to the top, And here's some more z-scores. So each side is the same here. And so I have my z-score in that very first column in both of them. So what the heck is in the middle here? And so the middle column really has a percentile in it of where the score falls in relation to the mean. And so that's this picture here. And so I can look at this percent number here, and it is the difference between a z-score of 0, which is the mean, the middle, and the z-score listed over here on the left. So you'll notice on this first one, a z-score of 0 is not different from 0 in any shape. So it says there's nobody between you and 0 because you are at 0. Okay, so think about this second column as a distance piece. So it tells me how far away I've walked from 0. And so my little race car example, this is how far the little race car has moved from 0. And then the last one is how much is in the tail. So it's telling me how far away I would still have to go to reach the end of the distribution, which is actually infinity, but we're going to cut it off at 50. So one thing to notice is the two columns here, columns 2 and 3, add up to 50% in every single one of these. Because we're only talking about the mean, the middle, to us, wherever our z-score is, and then our z-score to the end. And so that's only half the distribution, so that's 50%. That's why it doesn't add up to 100, it's only 50. The other interesting thing to notice about the table, and I love to ask this question on the test, is that you will notice, if you just flip through it, that they are all positive. All of these numbers are positive. Why are they all positive? Because z-scores so clearly can be negative, right? So I could have a -1 as my z-score. Okay, so that is not the answer. If you get why are z-scores positive, do not say because there are no negative z-scores. That's a lie. Okay. And so remember the beautiful thing about the normal distribution is that it's symmetric. So it's a hot dog fold. The positive numbers and the negative numbers are exactly the same. And so this table, you could add negatives to all the front of these and it would give you the same percentages. And so they only give you the positive half because the negative half is the same. Now, the problem with that is that, that when you're trying to graph these out and answer some of these questions, the negative half is the same, but it's mirrored. So let me draw you an example here. Alright, so on the positive side, I have my terribly drawn normal curve. And then this is column 2. It tells me how far my little race car is away from Z. Okay. And then this is column 3, where I have this line here is always 0. How far away is the finish line, or the end of the distribution. Okay, so this is always 0 here in the middle. And that's what the picture looks like on the top of a Z chart. How far am I from 0? How far am I from the end? The issue is that if I'm going to talk about the negatives, here's 0 still. Now on this one, it is how far is my little race car from the middle, but now that's still in the middle of the distribution. Right? So it's how far have I moved away from 0 to the left. And then for this one, here's 0. Here's my score. It's how far am I from the end. So these two things from the top to the bottom here are the same. It's just that when you're thinking about negatives, it's mirrored. It's because this is symmetric. So don't think about column 2 as left piece, then right piece for column 3, because it's left and then right, because then you will get them totally backwards when you try to do negatives, because it's now right left. So always think about column 2 as the middle of the distribution. It is from 0 to where you are. Okay, so it's how far have you wandered away from the middle of the room. So it's always about the middle. And then the column 3 is always about the edges. So how far, much farther do you have to walk to get to the end of the room, okay, or the end of the race? And so that's true on both positives and negatives, is how far away till the end. And I think that's probably the thing that people miss the most in this section is the negatives and calculating the percentiles, because they want it to be column 2, column 3, and instead column 2 is always in the middle, column 3 is always on the outside. So just kind of try to keep that straight. And we'll do a bunch of examples. Alright, so we can use this table to calculate the normal curve, percentiles, and with that, there is a rule. So something to help kind of make this easier on you. It's called the 34-14 rule. And so at one point in class, I said something like, the point of standard deviation is it tells me, on average, how far away are people from the mean. And I said it's a very specific percent. And so the biggest chunk of data is right up next to the mean. Well, now I can tell you that it's exactly 68%. And so most people fall one below the mean and one above the mean, which is -1 z-score and a +1 z-score. And that's approximately 68% of people will be within those ranges. So when you're interpreting standard deviation, it's really easy to think about it as one up and one down, because that's where most of the people are. So that's the 34 part. There's 34% of people between 0 and 1. So let's prove that to you. If I go back to our fancy table, if we wanted to look up a z-score of 1, I'm going to scroll down till I find where z here in this first column is 1. There it is. Okay. And if I want to know how far away from the middle I am, it's going to be the second column. And so you'll see that it's actually 34.13%, but close enough to 34 for this rule to count. And remember that the whole shebang always adds up to 50, so we've got 34 and 16, basically. Okay, so 34% of people are between 0 and 1 on both sides, because this is symmetric. So it is, for -1, it's the same thing. Okay. So where does this 14 thing come in? Well, 14% of people are between 1 and 2. And so if I wanted to know how many people are between 0 and 2, I could just add these two together. So it would be approximately 48%. So if I flip back to my z table, let's find 2 on here. Scroll down until I get to 2. And so it's added together. I've got 34%, 14%, the whole thing's 48. It's approximately 47.72, but it's close enough to 48. Remember, it adds up to 50, so 2 over here. So what they've done is just kind of giving you a very simple rule that is close enough. So 34% between 0 and 1, 14% between 1 and 2, and the leftover 2% out there from 2 to infinity, okay. Which is close enough to 3. Okay. Add 3 standard deviations, the numbers are so tiny that it is minuscule from 3 to 4 to 8. Okay. And so hang on to this 34-14 rule, because a lot of the questions end up being how many people are between 0 and 1. You don't even need to look at a table, it's 34%. It's close enough to 34%. So that rule is just to kind of help you estimate. So if I told you my score was 0.5, so that would put me here, I could probably estimate that it would be 17%, because that's halfway between 0 and 1. So if I go and I look at my z-score for 0.5 over here, I am close, right? It's 19%. But I knew it most certainly could not be 47%. That's right. So this is kind of where we're going to stop, and this is the slide that you saw earlier. So what we'll do in class together is talk about finding just plain old z-scores, finding the raw scores if you're given the z-scores, and then really work a lot on these percentages. Because sometimes it's just a struggle for people to kind of get what they are, and so we'll practice a bunch of different types. So you can try the homework if you want, but I might tell you to wait until we've kind of been able to go over this some more and do some examples in class where it's not me terribly drawing with my little PowerPoint pen, and we'll be able to do each one of these types and really get into like, why would I care about these percentages? Because the point of the whole thing, remember, is hypothesis testing. I want to show that my null hypothesis is so low in probability that I would reject it. And that's what I want. I want to reject, and let's say my null is false, so I can say that my research is supported. And so if I can find these percentages, I can tell that the null is really unlikely. So I can figure out where my finish line is for my little car. Alright, so be sure to go and take the little extra credit quiz that says that I've watched this thing, I know what's going on, at least maybe a little bit. And then in class next time, we'll do a bunch of examples. But if you want to look ahead, it has a bunch of examples that sort of walk you through different problems. We'll do these slides as well.